Hello, welcome in this presentation about Trusted Platform Module support in oVirt. My name is Milan Zamazal and I made this work together with my colleague Tomáš Golembiovský. This is going to be a quick overview, but the slides contain all the important information, so you can refer to them again later if you'd like. What is Trusted Platform Module, or simply TPM? If you had never heard about TPM before, you may have heard about it recently in connection with Windows 11 security requirements. TPM is a hardware device providing some security-related functionality that helps securing your computer. You can use it, for instance, to check that your firmware or software hasn't been modified by unauthorized parties, and the check can be performed for yourself or even for remote parties. Or it can be used for secure key management and storage, which is typically used by disk encryption. TPM support was added to oVirt this year, and it can be used for any purposes, but the typical usages expected are to be disk encryption or securing Windows boot. TPM in oVirt is a fully emulated device. It has its advantages. For instance, you don't have to have any TPM hardware on your hosts, or you needn't worry about problems with TPM chip supplies. The modern TPM standard 2.0 is implemented. Each TPM device has a small amount of secure persistent memory. Its size is dependent on the particular device. It shouldn't be any issue with virtual devices. TPM is emulated by an external emulator called Software TPM, which is used by QEMU. Software TPM keeps its data on a host local file system. In order to use TPM in oVirt, your VM must use UEFI firmware type and must be on cluster level at least 4.6 to have full TPM support. TPM is disabled by default. You can enable it for a VM in the VM edit dialog in the resource allocation tab, as shown in this picture. Once the VM starts, you can see its TPM device in the device tab, among other devices. A related functionality is Secure Boot, which is a UEFI protocol that helps preventing running untrusted code during boot. It also contains a small amount of secure non-volatile memory, which is used for storing the signing keys. Again, this persistent data is stored on the host in local file system. You can enable Secure Boot again in the VM edit dialog by selecting the corresponding firmware type. Why do we mention Secure Boot here in the presentation about TPM? Secure Boot is not a new oVirt feature, but a new feature is that its persistent memory is actually persisted. This has been implemented together with the TPM persistent memory. We call the TPM and Secure Boot persistent data VM external data because it is stored outside the VM in the localhost file system. This data must be managed by oVirt some way. While a VM is running, the data is managed by libvirt, including migrations to other hosts. But once the VM goes down, we must store it somewhere else than on the host local file system, so we store it in the engine database. It can be also stored on storage if we made exports, snapshots, and so on, which must contain the data in order to work properly. We use the same mechanism for handling TPM and Secure Boot non-volatile memory data, but the data itself is handled independently in separate actions and calls. Where do VM get their external data from? If you create a VM from an export or template that already contains some external data, then the data is copied from its original location, and it's the same. If you create a completely new fresh VM, then the data is created initially by the emulators and then stored in the engine database. If you disable TPM device or disable Secure Boot, then the data is deleted from the engine database immediately. You get a confirmation dialog if you do that from the web UI. But the data still remains in snapshots, exports, and other places where it was previously stored. It's only removed from the engine database. The challenge with handling VM external data is to ensure that the stored data is what the guest OS expects to see, to have the same version. When a VM goes down, we have the final data and we can copy it to the engine database. In addition to that, we also copy in the data periodically from a running VM. This is because something bad can happen to the VM, and then we may not be able to retrieve the data after the VM goes down. In such a case, we have at least some recent version. Generally, things like QEMU crashes or guest OS crashes are not a big problem as long as the data is not inconsistent in the guest OS itself. We copy it after the VM goes down. But it can be a problem when a host becomes unreachable or VDSM stops working, then we have no way to retrieve the data and we must rely on the periodic updates and use the last one available. There is also some risk to have stale data after powering off a VM from engine, but generally when you press the power off button on a computer, there are no guarantees about anything. If there is anything to cause trouble, it's snapshots. They are always tricky and TPM is no exception. Here we want to have in the snapshot the data that the guest OS saw at the moment the snapshot was taken. If the data in the snapshot doesn't correspond to what the guest OS expects, then it can cause trouble when booting the VM from the snapshots, because the guest OS can complain about security evaluations or have other problems. This is not a problem with offline snapshots, which are taken at the moment the VM is not running, so we simply can copy the data from the engine database to the snapshot. But it's different with live snapshots. Here we must rely on the periodically retrieved data, and the data stored in the snapshot may be stale if data in the guest OS was updated recently. For this reason, I recommend the following. Wait at least 2 minutes after external data changes before making a snapshot, or make multiple snapshots to be sure. You can also make an additional snapshot before doing big actions to the VM like upgrades in order to be able to return back to the previous state if something bad happens, which is advisable generally. When making snapshots with memory, it's basically the same recommendations for secure boot. It's simpler for TPM because snapshots with memory are disabled when TPM is enabled. This is because in case the guest OS RAM is inconsistent with the state of the emulator, then bad things can happen in the guest OS. VM external data is of course sensitive data. When you use, let's say, a desktop computer with TPM, then the data is stored in the secure TPM location and it's difficult to retrieve it from. With emulated devices, it's different. The data must be stored elsewhere. That means in the engine database or on the storage in case of export snapshots and so on. When a guest OS using sensitive data is running, the sensitive data can be stored in RAM or in core dumps and such locations. With virtualization and emulated devices, the data is additionally stored in the file system as already discussed. So in order to make the data secure, only trusted users should have access to it. That means access to the engine database, to engine logs, root access on hosts, or to the storage. In future, we may consider adding a new permission that would allow only certain users to export the data to storage, like making snapshots for VMs with external data. oVirt provides a feature to secure the data using a password, and people sometimes ask why we don't use that feature. The problem is that the password must be stored basically in the same locations as the sensitive data, so it doesn't enhance security really in the oVirt use case. So let's summarize the current TPM limitations. Live snapshots don't have guarantees that the stored data corresponds to the very recent data from the guest OS. Snapshots with memory are disabled when TPM is enabled. VM external data is not exported to export domains. Export domains are deprecated in oVirt. You shouldn't use them and you should use data domains instead. TPM can be enabled only for guest operating systems that are known to handle it properly. That means RHEL from version 7 and Windows from version 8.1. If you need to enable it for other guest operating systems, you can do that by changing engine OS info properties. And again, don't forget about security. It's not only about making BitKeeper happy that it has an access to TPM, but also making you happy that your BitKeeper keys cannot be stolen. What do we plan for future? Currently, sensitive data, not only VM external data, but also other data can be present in engine debug logs. Until this is fixed, you shouldn't allow untrusted users to access engine debug logs, and you shouldn't enable engine debug logs in production environments. Once libvirt implements synchronization guarantees, we can add support for snapshots with memory, even with TPM. Regardless of that, there is still space to make better consistency guarantees for VM external data in snapshots. And the new permission for exporting VM external data to storage may be added. Here you have some links to useful resources, links to feature pages for TPM and secure boot non-volatile memory. They contain a lot of technical details behind the decisions we made and how things are implemented. Software TPM emulator used by QEMU to emulate TPM devices. tpm2 tools. These are command line tools that you can use on Unix systems to play with TPM in the guest OS from the command line. And finally, Clevis, which is a popular disk encryption helper for Linux, and it can also use TPM for managing its keys. Thank you for watching this video, and if you have any questions, you can ask them immediately in the conference chat or anytime later on the oVirt users mailing list.